So what we're going to look at in this video is we're going to look at inverse Laplace transforms. The inverse Laplace transform is something that we're going to need in order to solve differential equations using Laplace transforms. So we want to introduce it, kind of figure out some algebraic techniques that we can use in order to find the actual function given the Laplace transform. And that'll really help us when we go in and do differential equations using Laplace transforms. For the purpose of this video, these are the Laplace transforms that I'm going to be using in order to do the work for inverse Laplace transforms. Now, there are more that we're going to see a little bit later on, like with the first and second shifting theorems, the unit shifting theorems, and periodic functions. But for right now, we're going to use these basic ones in order to introduce the idea. We're going to represent the inverse Laplace transform as, we're going to call it L inverse of big F of S. So big F of S is actually what the Laplace transform is. We're going to invert it, and then we're going to give it back our F of t, which is our original function. And what we're going to do is we're going to be using addition, subtraction, scalar multiplication, and partial fractions to modify the Laplace transform so we can find our inverse. So let's take a look at an example. Let's find the inverse of 3 over s squared plus 4. What I'm going to notice is I'm going to notice that the Laplace transform of sine of bt is going to equal b over s squared plus b squared, where b is a constant. So what I want to notice is that this is in the form of that sine function, right? It's got the constant over s squared plus some value. Now, this is one of the reasons why it's so important to actually go through and create some Laplace transforms and practice that skill and to memorize the table of the basic Laplace transforms so that you can recognize your inverses when you go in and have to find the inverse. So we've got that, and we're going to notice that in this case, b squared is going to equal 4, right? That's right there. So that means that b equals 2. Now, if I look at my function, I'm going to note that I don't have a 2. In fact, I have a 3. Okay? So what I need to do is I need to actually separate that out into two distinct values, two distinct numbers, in order to give me 2 and some scalar. And then what I'm going to do is I'm actually going to go in and I'm going to factor out the scalar. So I know that 3 halves times 2 is going to equal 3. Okay? And basically, if you just took 2x equals 3, the number that you want times some variable x equals the number that you have, that should give you your scalar. In this case, it's going to end up being 3 halves. So that means that I'm going to have L inverse of, and this will be 3 halves times 2 over s squared plus 4. Now what I can do, because the Laplace transform and its inverse is also going to be linear, I can pull out the scalar. So that means that I get 3 halves times the Laplace transform of 2 over s squared plus 4. What that tells me now, because b is 2, this is going to be 3 halves sine of 2t. And that is, in fact, our inverse transform. Let's take a look at another example. So now let's take a look at another example. In this case, what we're going to do is we're going to use a property of addition. So we're going to have L inverse, right, 4s minus 1. And I'm going to look at 4s minus 1 and for s squared plus 9. And that's going to just be 4s over s squared plus 9 minus 1 over s squared plus 9. And the reason why I did that is because I do know that I have 2 functions that have Laplace transforms that look like the individual pieces. So on the one hand, we have cosine of bt is going to equal s over s squared plus b squared. And I have sine of bt, and that's the Laplace transform of sine of bt equaling b over s squared plus b squared. In this case, I could see that b is equal to 3. And what I'm going to need to do is I'm going to need first to go and factor out, factor out the 4. And that gives me 4 times s over s squared plus 9. And then minus, and we're going to do the same thing that we did before. If you remember, we need to have a 3 now in the numerator, okay, in order to have the proper inverse. So I'm actually going to say, okay, well, if I need a 3, what that means is that I'm going to get 3x equals 1. So x should equal 1/3. So what that gives me now is that's going to be 1/3 times 3 over s squared plus 9. And then we'll pull out that 1/3, and that'll become our scalar, or actually a negative 1/3 in this case. So now my Laplace transform can be rewritten as 4 times s over s squared plus 9 minus 1/3 times 3 over s squared plus 9. And then I can break that up, and I now get 4 times the inverse Laplace transform of s over s squared plus 9 minus 1/3 times 3 over s squared plus 9. And that's also a Laplace transform, excuse me. So now this ends up being 4, and it'll be 4 cosine 3t minus 1/3 sine 3t. And that, in fact, is the function that we got our Laplace transform from. Let's take a look at finding the Laplace transform for 8s squared minus 4s plus 12 over s times s squared plus 4. In this case, I don't actually have a Laplace transform for s times s squared plus 4. But I do have something for s, or 1 over s, and also either s over s squared plus 4 or 2 over s squared plus 4. And in this case, we're going to use our b, knowing that our b is going to end up being 2. So the Laplace transform for simply 1 is going to be 1 over s. And the Laplace transform for cosine bt is going to equal s over s squared plus 4. And the Laplace transform for sine of bt is going to equal 2 over s squared plus 4. So in this case, what I have is I have the multiplication of two expressions where I do have a Laplace transform that will match them. So what I'm going to need to do is I'm actually going to need to break this apart. And the way that I'm going to do that is I'm going to use partial fractions. Okay, I'm going to utilize partial fractions. And so if you need a review of partial fractions, go ahead. I have some videos on partial fractions, or there's some great ones out there. What I'm going to do is I'm actually going to show you what it is that we get for 8s squared minus 4s plus 12 over s times s squared plus 4 when we break it up into its partial fractions. So 8s squared minus 4s plus 12 divided by s times s squared plus 4 is going to end up equaling 3 over s plus 5s minus 4 over s squared plus 4. So now what I have is I actually have something where I can take that inverse, or I know what the inverses are going to be. And I'm going to separate that out even more. I'm going to get 3 over s plus 5s over s squared plus 4 minus 4 over s squared plus 4. Now, I want to get this to be a 2 in order to make it my sine of bt. So what I'm going to get, I'm going to take a 2 times 2, that'll equal my 4. Okay, so the scalar we're going to pull out is going to be a 2. So if I rewrite this, this is going to be 3 over s plus 5s, or 5 times s over s squared plus 4 minus 2 times 2 over s squared plus 4. And remember, whenever we have a sine, or the sine of bt, we need to get the value in the numerator to equal the square root of the constant in the denominator. So now I actually can rewrite this. I can rewrite this as 3 times the inverse Laplace transform of 1 over s plus 5 times the inverse Laplace transform of s over s squared plus 4 minus 2 times the inverse Laplace transform of 2 over s squared plus 4. Now I can go in and just rewrite or put in my functions, and that gives me 3 times 1 plus 5 cosine 2t minus 2 sine 2t. Or we could just rewrite this as a 3. And there we are. Now what we've done is we found the inverse Laplace transform. We found the original function that we got at the beginning. So what I've done here is I've utilized some basic properties, and the basic properties that we're going to be using repeatedly for finding inverse Laplace transforms or for basic functions. We've got, on the one hand, you can do scalar multiplication, right? You have to just find the right scalar, and you can use the method that I put out here. 2, you can go in and you can break two pieces apart using addition or subtraction. And 3, we can use partial fractions. And those are our basic techniques. This is Dr. George Sweeney, and I want to thank you for watching my video. If you found it helpful and you liked it, go ahead and click the thumbs up. If you want more of these videos and you want to get my updates, please click subscribe. If you have any questions or you just want to say how much you really enjoyed the video, go ahead and leave some comments. I do read and respond to the comments.